All right, this is actually problem number 9 on page 348 of your textbook. We're going to use the Euler method and the improved Euler method to estimate y of 0.5 for this particular differential equation that I have written there. So we have y prime is equal to x minus y quantity squared, and the initial condition for us is given that at x equal to 0, y is equal to 0.5. So let's set up our spreadsheet for the just for Euler's method to start with. Remember, our first column we'll just put in the step. We're going to start this with a step of 0.1 and be able to change it later. So we'll put 0.1 in there, and then I'll just hit equals that particular cell right above it, because what that'll allow me to do is if I change this cell, A2, it'll let me change all the cells below it if all I do is just copy this particular cell down. All right. So again, just to show you, if I change the step size in this first one, it'll change all of them, and I don't have to retype everything in or recopy everything down. I can just retype it as I need it. All right, so our next column are our x's. I'll just label it as x sub n, and the next column over I'll label as y sub n. Remember, in our first row, we're going to have this as our initial condition. So we'll start at when x was equal to 0, y was equal to 0.5. So in the next column, we're going to compute our slope. Remember that our slope, with Euler's method and improved Euler's method, and with Runge-Kutta method, which we'll have a different video for that one, all of those are using basically lines to approximate what the curve needs to be. For Euler's method, we're just going to use the tangent line to start with, and then as we move across with little line segments, we will use that slope at each of those points at the end of the line segments to help us approximate the curve. So we'll need the slope, so that's what we refer to as the f of x sub n, y sub n. So we'll do that computation here. Notice that it's the quantity x minus y squared, so I'll need to use a parenthesis. I'll go over and grab the x value minus the y value and square it. That will be the slope of our line segment that we're using to approximate the curve at every point. In this particular case, it's at our initial condition, but that's the slope of the line segment that we're going to use at each point to approximate the curve. And that's how we're going to move along to get an idea of what the graph of the curve would look like. And then, so for Euler's method, we compute our new y, so we'll call it y sub n plus 1. Remember, that's equal to the old y plus the step size times the slope. Which makes sense again, because remember, we're just trying to move across our x values in little increments and then figure out how the y moves. And so this is literally just the equation of a line. This is your old y, this is your slope, this tells you rise over run, this is telling you how far you're running. So that formula makes sense from what we know from just high school algebra. So there is our new y value. We're going to copy that new y value over into this column. And for our new x value, remember, all we need to do is add the step to the previous x value. So I'm going to grab the previous x value and then add the step, which is right next door. Or I can grab this one. It doesn't really matter, because all we're going to do is copy it down anyway. So then I'm going to copy these two cells down to the next row. Remember, I can just do that by grabbing over on the little box on the corner until it changes to a more solid, or a black plus sign as opposed to a white plus sign. And then I will grab this row and copy this whole row down. And this now gives us estimates for the y values at particular x values. What we're looking for in this problem is the estimate at x equal to 0.5. So our y value there would be approximately 0.5639, roughly. And again, when you're turning these in for your take-home, you're going to be turning it in with just as a file anyway, so you don't need to bother writing down the answer. You can just highlight on the screen which one it is. And again, just to illustrate how we can use this to get an idea of what the curve has to look like using the sticks, I can just, using those line segments, we can highlight the points that we're interested in, and then we can insert a chart. And we want to use one of these line charts here. And we'll just use the scatter chart here, which shows me the line, and see we can actually see on here how it's using line segments to try to get an approximation of what the curve has to look like. Again, the real solution for this is probably, it's either below it or above it, or maybe it crosses it. We don't know because we don't really know what the curve looks like. If we had, say, graphed a slope field or actually had the honest to goodness exact solution, we could put that on here too and then see how they compare. But this the idea again behind these methods is to try to get an idea of what the curve, what the solution looks like in a small interval around the initial condition that we're given. Let's see how we could modify this to do improved Euler's. Remember, improved Euler's is trying to do an average of the slope. Let me just delete this chart out of the way. So improved Euler's method, we don't use this as our new y. We're using that y values for our Euler method as an intermediate step. Then we will use that intermediate value and the next x value. So I'll write it as f of x of n plus 1 comma y sub n plus 1 star as our next slope. I'm going to spread this out just a little bit so I don't run out of room. Maybe. There we go, a little bit bigger. All right, so for this one, I want the next x. So we still use our slope formula, which is over here, but we want to use the next x value and our next y value to get the slope estimate. So I need to use B3 here, not B2, because that's the next x value. And I want to subtract off the intermediate y value, which we computed in E2. And we want to square that because that's our formula for the slope, the formula for the dy dx. All right, so now we're going to use that. This is, we have these two slopes. So I'm going to make a column for average slope, which will just be the two slopes, D2 and F2. Whoops, forgot to hit the plus sign. D2 and F2, and divided by 2. That'll be our average slope. This is now what we're going to use for the change from our old y value to the new one. So our new y sub n plus 1 will be equal to old y, which is in C2, plus step again, 0.1 times our average slope, which is what we have there. And then there's one more modification we need to make, because we need to make sure we copy this new y value down here rather than the one we had before. So we want equals h2 instead. Now we need to copy these down and then take this whole row and copy it down instead. All right, so now we've got our estimates here, and we see that for this was Euler's method here. Improved Euler's method did change it a little bit. So using improved Euler's method, using improved Euler's, we get, if I can write, y of 0.5 is approximately 0.5503. So that gives you an example of how we can use Euler's method and improved Euler's method to help us get approximate solutions to differential equations.